To pediatric grand rounds. And I'm going to hand things off to our Vice Chair for Education, Dr. Sandrain Van Schaik, to introduce our speaker for today.
Hi, welcome everybody. Sorry, noises in the background here. Welcome everybody. It's my great pleasure to introduce Dr. Anita Moon-Grady, who, when we just chatted, said, well, the introduction can be brief. You can just say, we've known each other forever. That's true. But just for people who don't know her, haven't known her forever, Dr. Anita Moon-Grady is the director of the Fetal Cardiovascular Program at UCSF Benioff Children's Hospital. And she uses her training in pediatric cardiology and neonatal perinatal medicine to raise awareness and increase detection of fetal heart problems. Working in concert with the UCSF Fetal Treatment Center, she coordinates care for pregnancies affected by fetal heart disease or dysfunction, whether intervention is necessary before, during, or immediately after birth. Her research focuses on non-invasive imaging modalities for investigation of normal and abnormal cardiac function in patients with congenital heart disease and fetuses with congenital heart disease and cardiac compromise, as well as fetuses with cardiac dysfunction due to non-cardiac causes. Dr. Moon-Grady earned a medical degree from Stanford University, where she also earned a Dean's Award for Research in Human Genetics. At UC Davis, she completed a residency in pediatrics and a fellowship in neonatal perinatal medicine, and then a fellowship in pediatric cardiology at UCSF. She's a member of the American Society of Echocardiography and the American Medical Association. She has been elected Fellow of the American College of Cardiology, Fellow of the American Academy of Pediatrics, Fellow of the American Institute of Ultrasound in Medicine, and Fellow of the American Society of Echocardiography. And she served on the boards of the Pediatric Council of the American Society of Echocardiography, the North American Fetal Therapy Network, and the AUM. She is the founding vice president of the nonprofit Fetal Heart Society and chair of the Ultrasound Practice Accreditation Committee for the American Institute of Ultrasound in Medicine. So in addition to being a phenomenal cardiologist and researcher, also really a role model of national leadership. She told us that only 30% of fetuses with complex congenital heart disease are recognized before birth. The others are born in regions where cardiac care is sparse or unavailable and may present profoundly ill, making long-term neurodevelopmental and functional outcomes poor, even with excellent surgical outcome. Over 90% of heart disease should be detectable in the second trimester of pregnancy. And this really has motivated her to do her work in machine learning and AI to assist clinicians as this holds great promise for improving prenatal detection toward this goal. So with that, I'm handing it over to Dr. Anita Moon-Grady.
Thank you so much, Sandrine. I would have been happy with known her forever, but thank you so much for the introduction. And good afternoon, everyone. It's my pleasure to be here to talk about how we are using artificial intelligence to advance diagnostic excellence in fetal imaging. I have no financial disclosures. And excuse me. In the next 50 minutes or so, I hope to convince you that artificial intelligence has the potential to help us in medicine in all of the domains of diagnostic excellence, including accuracy, timeliness, reproducibility, robustness, and availability. The advantage of artificial intelligence in medicine, just in addition to all of these domains, it's especially given its ability to scale, the availability and potential to narrow disparities in health equity and to democratize care is what's really drawn me to this. So the availability is really important. So what is artificial intelligence? Well, it's actually a little controversial, but most agree with some version of this Venn diagram. And in 1959, Arthur Samuel, who's a computer scientist, pioneered the study of artificial intelligence and described machine learning as the study that gives computers the ability to learn without being explicitly programmed. And we are already actually living with this every day, including spam filters, speech recognition, Google searches, Facebook ads, stock trading, So this has really crept into everyday life. Put simply then, machine learning is a subset of artificial intelligence where the machine is trained to learn from its past experience. The field has expanded in many ways that we won't be able to cover in this short period, so I'll mostly be focusing on the medical applications, but really the applications of machine learning are immense. I'll be specifically talking about cardiology a little bit later in the hour. And for an interesting and up-to-date paper in this article, Rima Arnold, who's been my colleague in this, and her colleagues reviewed the state of machine learning in cardiovascular care. And among the highlights of this bibliometric survey that appeared in Journal of American College of Cardiology was the cornucopia of current applications and use cases for machine learning, from auto ejection fraction to machine EKG interpretation to the Apple Watch. And they highlighted a growing number of publications and, excitingly, a robust collaborative attitude. This has really been an international effort. They also, in the paper, pointed out how quickly the field is moving, not only through the huge boom in just the last 3 to 4 years, but also in the volume of papers appearing as preprints. I did my own less than scientific search and found over 1,000 articles in cardiology that have been published in the last few years using machine learning. There are fewer in echocardiography at about 250, largely because of difficulties with image quality and movement of the patient and the heart. And there have only been a handful that have shown up for fetal cardiac diagnosis, less than a dozen. But let's step back a little bit and talk more about what exactly machine learning is and how it applies to imaging. As I said earlier, rules-based algorithms apply rules to data, and machine learning algorithms learn patterns from the data. There are several types of machine learning algorithms, including statistical machine learning and deep learning or neural networks. These neural networks are a type of machine learning algorithm that are especially useful for complex nonlinear data, such as medical data. And then further, the machine learning using neural networks can be supervised, unsupervised, or semi-supervised. And common tasks then can include data classification, segmentation, and sequence prediction. So to look at it another way, there are two concepts that we are most familiar with in medicine: data mining used for discovery, and machine learning, of which deep learning is a subset. The key general concepts of machine learning include supervised learning. This is task-driven, where the computer is presented with example inputs and their desired outputs, labeled with the ground truth by humans. So the inputs and outputs are labeled, and the model learns a general rule to map inputs to outputs. Unsupervised learning is better for clustering. Here, no labels are given to the learning algorithm, just a bunch of data, leaving it on its own to find structure in the input. The model then can categorize new input based on similarities and differences to the training data, and that will inform the output. Reinforcement learning is a computer program interacting with a dynamic environment in which it has to perform a task or goal, something like self-driving cars, but I'm not going to cover this any more than that. Deep learning uses more than one layer between the input and output, and the layers in between are hidden. It's also supervised, semi-supervised, or unsupervised. And so I'm going to focus now down on just this issue of deep learning, which is a subset of machine learning. Hopefully that's clear. So the deep neural networks have already been shown to be accurate in many types of tasks, from object detection to speech recognition. They can learn automatically without predefined knowledge explicitly coded by the programmers. And there are a vast number of available neural networks and combinations of neural networks where each architecture is designed to perform a given task. How does this work? Well, I'll highlight just two concepts with regard to the different types of neural networks. There are recurrent neural networks and convolutional networks, or CNNs. The standard uses of recurrent neural networks occur when practitioners are working with time series data or sequences. So there's the input and then the algorithms, and their output is what is most likely to come next. So this is the type of machine learning one might expect in the intensive care unit and trying to identify patients who are at risk of deteriorating. Convolutional, excuse me. Convolutional neural network is a multi-layered neural network with a unique architecture that's designed to extract increasingly complex features of the data at each layer to determine what the output ultimately is. And so this type of neural network is better for being presented with something, and the model will say, oh, this is this, or this is not that. So we can either do the what's going to happen next, or we can say, well, here's a thing, what is it? So those are the two key concepts. The data science itself actually resembles a variety of statistical concepts that we're already somewhat familiar with in medicine, including linear regression, logistical regression, Bayesian analyses, et cetera. So these are not foreign concepts to us. It's comforting, I think, to look at it that way. The models can be built into different classifiers or schemes. So these are just an example of different types of classifiers that have been developed. And one can compare the performance of these types of classifiers by using standard data sets consisting of training data sets, validation data sets, and test data sets. So in this example, for instance, this is the MNIST database. It's an open source, freely available database of handwritten numbers that contains 60,000 training images, 10,000 testing images. And using this, one can compare error rates in testing after the initial training period and test across different models using the different classifiers to decide which one is best, or to further refine the models by comparing error rates. So handwriting is easy, but what about medical imaging? In September 2017, I was introduced to Rima Arnaut and her lab. They had been using convolutional neural networks and a supervised learning approach, and they were able to train a model to recognize and classify 15 views from adult echocardiograms. The model classified views with up to 97.8% overall test accuracy without overfitting, which I'll come back to. This is what the 15 views looked like, sort of standard echo views. The model did better with video. The video is the dark blue bars, and the model looking at still frames are the light blue. But both were better than the human counterpart, the human expert, who's shown in the white bars in terms of accuracy in some of the domains. Given that this type of deep learning is, as I said, a black box in terms of what's in between the input and the output, I find it helpful to simply ask, what is the model seeing? So I'm going to just divert a moment here to show some of the methodology on the back end. In their paper, the data visualization experiments were done in the form of saliency mapping. So on the left is the downsampled ultrasound picture, and on the right is the salient features that are being labeled by the black box. And so this is the output. And I think you can appreciate that what the model is, quote unquote, seeing is similar to what our eyes would see. Furthermore, the model has trouble identifying the images when key areas of the frame are covered up. as shown in the decrease in model confidence in this slide on the right, the model confidence being 92% when you can see most of the image, and down to 11% when the image is covered. So the model does seem to be seeing what humans are and performs similar to, but better than the human experts. The model actually also did better than humans when the images were downsampled significantly or when imaging conditions are suboptimal. And as another aside, this illustration shows a non-medical version in more detail how the saliency maps and so-called gradient class activation maps or GradCam maps can allow you to visualize how a CNN model makes a decision. And these are especially helpful if the decision is incorrect. So I'll guide you to the illustration on the left showing salient pixels or features and how a model might incorrectly interpret a picture of a volcano as a round mirror. The GradCam shows the correct prediction here of a cat, but incorrect prediction in the middle frame of it labeled it as an airliner, which is interesting. So correct identification, incorrect identification. It's easy to see where the model is going wrong there. All right. So medical images are imperfect, and so there's also this concept of probability assignment. The model performs well when the images are not perfect, and examples of suboptimal quality images are shown here for each view. This is a fetus, and along with it, we've shown the violin plots, which show the confidence probability assigned to the suboptimal image. And it may be that if we say we're to set a very high cutoff or standard for confidence in the model, that we can get better than the human eye when imaging conditions are like this, such as small fetus, unfavorable fetal lie, or maternal obesity. So I personally am gradually becoming aware not only of the clinical uses of this technology, but also its limitations. First of all, the models are very data hungry, and the more data you have, the better they will perform. As I said, 60,000 images were used just to train for handwriting of basic numbers. But there also has to be diversity in the data set. And so this can hinder the generalizability, say, if it's only trained on images from one center, no matter how many images you have, it may not perform as well on images from a new center. But honestly, this is true of humans too. For our cardiology fellows, if you train in pediatric echo, you have trouble interpreting adult echoes initially because the image is upside down, right? So if you train in both at the same time, you could probably interpret them equally well. So the models are not that different really from humans. Now, supervised learning not only requires a lot of data, but also requires human experts to label the data for training and validation sets. And how large are these data sets? I'll come back to that later, but it's approaching in the millions, I think, at this point for this project. So now another issue is called overfitting, and I want to spend just a minute on that. It seems to be one of the biggest fears and kind of cardinal sins in the data science world. So graphically, shown here is where a simple fit is fairly good. One that adds dimension, such as the log transforming, for instance, that may be a better fit. But once you try to get a perfect fit, the equation starts to do a really bad job with prediction, if that makes sense. So reasonable fit good fit, overfit. And with machine learning, the model hits a point where it is doing extremely well on the training set, but starts to do poorly on a validation or a test set containing data that it's never seen before. Finally, there's bias in the training set, which if there is bias in the training set, you will lead to model bias. And that concept is very simply illustrated in this slide. This is a screenshot of one of my fellows, actually, their iPhone picked out all of these pictures of food for them. So this is an example of artificial intelligence, but wait a minute, one of these things, that's not food, that's a congenital heart specimen from the pathology lab. So that's kind of funny. I thought it was funny, but not so funny when big companies such as Google have to apologize for their apps making much more serious blunders. And so we need to keep in mind that bias in the data set can also bias our model. So now, knowing about the work in adult echo and the potential for AI in medical imaging, fetal cardiac imaging, which is labor intensive and prone to error, seems like an enticing area to explore in many domains of diagnostic excellence in imaging, including acquisition, identification, classification, quality improvement, and dissemination. Some recent work has addressed a few of these domains, including image acquisition. Work in the UK has demonstrated the feasibility of automated image acquisition, and also from the UK, a proof of concept paper in image recognition and annotation using filtering to account for high frame rates. They trained a classification and regression forests to predict the visibility, location, and orientation of the fetal heart in a larger image. And of those possible viewing planes, they labeled each frame and developed a novel adaptation of regression forests for circular variables to deal with prediction of systole and diastole, so to account for the movement of the heart during the exam. In the US, Lami Yo and Roberto Romero, working with the NIH, developed a technique for identifying and generating multiple cardiac views from a single volume data set automatically. Here, the operator acquires a volume data set with the ultrasound probe and is then prompted to label a set of 7 different reference points. And then the software auto-generates the images on the right, labeled with aortic arch and pulmonary valve and so forth. And then looking at this, one could potentially detect an abnormality. The valid concern, though, is that the user has to be able to obtain the image and also has to be able to recognize and mark the anatomical structures. But if they don't have the expertise to read and interpret what they've captured, then the resulting images are not as useful and maybe less successful in labeling than what was shown in their hands. So they suggested that a solution to this problem was to integrate the automated acquisition with a human expert interpretation, since the stick or volume data sets, diagnostic planes, and video clips could potentially be transmitted by telemedicine, and expert consultants could then evaluate the images locally. So after seeing that prior work and after seeing what had been done by Rima Arnaud, when she came to me wanting to collaborate on the pediatric echo, given her prior work with adults, I immediately thought that there might be a larger potential use for this type of image classification, artificial intelligence, machine learning. We know that prenatal diagnosis improves outcomes. Routine fetal ultrasound should detect 90% of congenital heart disease, but it only detects 30 to 50% of congenital heart disease in reality in Western countries, and even less in other countries. If deep learning technology can identify patterns in medical imaging, we proposed that deep learning could identify diagnostic views, quantify structure and function, and diagnose congenital heart disease on prenatal ultrasound of the fetal heart without operator input other than basic ultrasound acquisition skills. We made use of the now well-described axial planes, the abdomen, 4-chamber, 5-chamber, 3-vessel view, 3-vessel trachea view. These are standard axial planes that all obstetric imagers should be able to acquire. This is an example of a cine sweep. They can be acquired as individual still frames or as a single sweep containing multiple frames. And since this is part of every echocardiogram and should be part of every obstetrical ultrasound, we had a huge number of these digital images available. So our training set was 107,000 images, 107,000 images from 1,300 echoes and screening ultrasounds done between 18 and 24 weeks gestation. So the standard mid-gestation anatomy scan. And then using a supervised learning approach, we trained a VGG16 inspired convolutional neural network model to distinguish among the 5 views that I just went over. We then developed binary classifiers using the same network architecture to distinguish for each view a classification of normal versus abnormal. And then we created composite scores by which to classify the abnormal disease states. This table outlines the composition of the training and test sets. This is part of our publication if you're interested in looking at it, but I'll tell you what the important parts of it are. The training and test sets from normal fetuses and from 16 different types of congenital heart disease lesions. We had 2 different tertiary medical centers in the US contributing images, and the training set comprised 1,326 ultrasounds. Within each ultrasound are up to thousands of images, and so that's how we got to over 100,000 images. So the training set had 1,326 ultrasounds with 926 normal and 400 abnormal. And then we tested on a holdout test set that was 30% abnormal, a second holdout test set from the other institution with a larger percentage of abnormals. And then finally, and this is the best part, a large holdout test set from our obstetrics practice that consisted of 4,000 ultrasounds in which only 0.9% were abnormal, which is similar to the incidence of congenital heart disease in the general population. Our view classifier performance is shown here on the top left, is a normalized confusion matrix and ROC curve that showed the classifier performance on the CHD enriched data set. And just for reference, for those of you who can't see, the ROC curves are difficult to see because they are really, the AUC is approaching 1 for all 5 of the views. The violin plots that I've gone over before for this particular test data showed that when the predictions were correct over 10,000 times, the model confidence was quite high. And when they were incorrect, the model confidence was actually not that confident in its prediction. And so that's sort of what we expected. Now on the lower left, the normalized confusion, sorry, that's the violin plots. And on the lower left, is the normalized confusion matrix and ROC curves for that general OB test set. So top is an enriched for abnormal test set, and on the bottom is a non-enriched test set. And again, very good model performance. To validate that the view classifier used clinically relevant features, we performed mapping experiments on test images to show the saliency mapping and the GradCam mapping that was most important to our classifier in making its decision. Both experiments showed that the view classifier makes its decisions based on clinically relevant image features. So I particularly like the bottom row, which shows the GradCam, gradient weighted class activation maps, which produces sort of a heat map that highlights the important regions of an image using the gradients of the target in the final convolutional layer. And this is showing the aortic and ductal arches, aorta in the center. Here's left ventricular outflow tract for chamber, and the stomach is highlighted in this abdomen view. So great proof of concept there. And then on the abnormal fetuses, this is particularly gratifying. Shown here are the normal versus tetralogy of Fallot 3-vessel views, or the hypoplastic left heart syndrome versus normal versus tetralogy. The features that the model is identifying are exactly the features that that a human should be identifying, and these are thought to be the sources of screen failures, in that the operators generally don't recognize them as abnormal. Our previous work also showed some success with segmentation and how it can be used to perform common measurements like cardiothoracic ratio, cardiac axis. We can classify each pixel according to structure and then can calculate measurements based on the segmented structures. In practice, as we applied this to our data set, this image on the left shows an example input image. The ground truth human label is next. The model prediction follows, and then calculations of the cardiothoracic area and cardiac axis for normal heart, tetralogy of Fallot, aortic stenosis, and hypoplastic left heart are shown. The table on the right shows cardiac measurements, the actual numbers from the calculations, and the predicted cardiac axis, for instance, for a normal patient is 45 degrees, and for tetralogy of Fallot, left axis deviation of about 65. This is exactly what we would expect just from the teaching that we've been doing for decades about cardiac axis deviation and tetralogy, and the model was able to clearly identify that. We were further able to perform segmentation of an image in series. This is now multiple clips in a cine clip, multiple images in a cine clip. And this allowed us to plot chamber area over time in order to calculate function in the form of fractional shortening. So the conclusions from our study were that application of deep learning CNN models to routine guideline recommended clinically performed second trimester ultrasounds resulted in a significant improvement in detection of fetal congenital heart disease over the general population-based data that we have. Our design, though, highlights the need for domain-specific human expertise to guide the learning process. All of these hundreds of thousands of labels were done by either myself or by a trained, very experienced cardiac sonographer. So it's very tedious and time-consuming to do all the labeling in this supervised learning approach. And we think that setting an automated system that is going to err on the side of very high sensitivity and then uses human overreading to increase specificity may be the best goal in this type of prenatal screening and the use case for this type of model. Our work contributes to the image classification and diagnostic classification domains. And the field has really made a good start in the last few years. Feasibility is clear, but we haven't quite gotten to the quality and getting things through the FDA and disseminating widely. These are still targets. But with the last few minutes, I want to just step outside of fetal hearts just to show that we're not talking about science fiction here. In fact, There are several other groups in various stages of development of these types of models, specifically for fetal and obstetric imaging. Some are even commercially available, albeit in this one not in the US. They're available for both retrospective analysis and at the point of care. So this is one such model that's been developed to pick out the fetal face in a 3D volume data set and just present the image without any manipulation by the user. They're also marketing gynecologic applications and fetal brain. This publication showed the potential to automate first trimester nuchal translucency screening. This is done between 11 and 14 weeks on a very specific image with a lot of user training required and a measurement of this translucent area behind the fetal neck. And so this seems like a good target for the use of machine learning and AI assisted analysis. And so that is, this was from a paper. I don't know if that's clinically, commercially available yet or not, but has potential. And then there's this product, which unfortunately I have no affiliations to disclose. That's being released later this year for clinical use. And this is just a video from the internet where the sonographer is stopping and the algorithm is correctly identifying which part of the body it is, for instance, and then labeling the expected structures on the right-hand side of the screen. So very, very exciting. For use in cardiac, not quite there yet, although certainly they could use technology like we have used and build that into these recognition type of algorithms. The products here guide the user through the examination protocol and provide quality and completeness checks. And so although they're not yet able to flag abnormals or make diagnoses, that seems to be the next obvious step. So will AI replace doctors? Are the machines coming for our jobs? Are robots going to replace us in healthcare? Clearly, I don't think so, or I would have retired by now. But I will use an often used quote here to say that I firmly believe that while AI won't replace doctors, doctors who understand and utilize AI will replace those who don't. And with that, I am finished talking and am happy to take questions. I do want to thank Rima Arnold and the entire Arnold Lab for all of their work and support, and looking forward to working with them in the future. Thank you.
I am so sorry. I'm like looking for my mute button everywhere. Hi, thanks you, Anita. That was just awesome. It was a great talk. I am gonna see if there's actually any questions from anyone in the audience. And while we're waiting for that, I'm gonna ask you a question. I know that you can't really speak about like what's currently going on, but can you speculate a little bit, sort of like in your biggest hopes and dreams, where will this take us?
So this particular project has a very clear use case, and that is everybody has an ultrasound machine. Even in the United States, 99% of women get their recommended second trimester ultrasound. That's where you find out the sex of the baby and look for anomalies. And so we've previously shown in the state of California that even though 99% of women had the test, only 30% of the time was the heart disease recognized. And these are like AV canal or hypoplastic left heart syndrome. We're not talking about tiny VSDs. So there's some kind of disconnect between the people who are doing a perfectly good ultrasound with a good ultrasound machine and recognizing that it's not normal and that the patient needs to be referred for additional screening. So we've been trying to teach them at the point of care for decades, trying to show them how to recognize abnormalities, tips, tricks, and it's just not working. I think that the volume of normal exams that they do is just so high that the humans reach a saturation point and they just don't see the abnormalities. The models don't fatigue like that. And so if we were to put a model on the point of care ultrasound machine that recognized that the operator had gotten all 5 views and told the operator that all 5 views were normal, then they would be normal. But if they fail that screening, if either the 5 views can't be obtained or if one of those views is abnormal, then they would be referred. So we're taking that human error out of the equation and improving cardiac screening. And then we can also, it's not going to, depending on where you set your sensitivity and specificity, we don't think that it's going to increase the work for pediatric cardiologists all that much, because now we will no longer have to see very low risk women because they'll have their screening done by the model. So it takes very little training to just acquire the appropriate images. And we see the potential for this then to be able to be used at the bedside almost anywhere with almost any kind of ultrasound machine. There are now probes, some of you may have seen these, there are probes that you can use with your iPhone. And any place with internet connectivity, you could send the images to me and we could run them through the model. So it really has the potential to allow us to democratize really good obstetric care with respect to congenital heart disease around the world. That's a pretty lofty goal, but that's my goal. We'll start with the United States. We got to try to get the US better than 30%. But that's the ultimate goal, and to really bring good diagnostic care to people in remote rural areas, places without the kind of expertise that we have here at UCSF. I mean, this would be useless here at UCSF, right? I mean, we're not missing things. So the appeal is in the general obstetric low risk population that doesn't have access to a tertiary center. Sorry, long answer, but
no, I think it's great. I guess I have more questions from that answer, but I'm going to honor Dr. Phil Moore first, because he asked, would this have application to ER bedside ultrasound screening for all the reasons you just mentioned?
Mm-hmm. Thank you for the question. So the type of image recognition that we're doing is and proof of concept could then be taken to any ultrasound imaging. It started with adult cardiac imaging, and now we're doing this. The problem is that the models have to be trained to the specific images. And so if you said, oh, well, I want to use this in the emergency room to detect, poor cardiac function, so you can do that, but you'd have to retrain the model. So, so that's one of the drawbacks that I had on the slide, that these models are very data hungry and they're very labor intensive to develop.
And I think Dr. Ronald Kleiman has a similar question. He starts by saying, "Wonderful talk. In the examples where an incorrect diagnosis was made, was it due mostly to poor image quality or to variations in the angles of intonation that differ somewhat from the training set? So far, you have used 2 ultrasonographers to train the machines. Since cardiologists vary in their interpretation, how will your models work in other centers with different cardiologists interpreting the results?"
Okay. So I'll answer that second one first. Probably wasn't very specific. We were not training the model what to look at. We just said, this is a 4-chamber from a normal patient. Here you go. And the model could have been looking at anything on that picture. It could have been looking at the upper right-hand corner where it said normal. That's why we use the GradCam and the saliency mapping to make sure that it's actually looking at clinically important features of the image. So we threw tens of thousands of normal 4-chambers, and in these, the fetus could be lying any which way. So the angle of insonation doesn't really matter. Small subtleties of image quality they all sort of smooth out. We didn't give the model, well, we did give the model images that we thought were bad images and said this is a bad image, and so trained it, to reject these non-target sorts of images. So yes, good question, but we think we've gotten through that bias. And one of our next steps is that we're working with the Fetal Heart Society to get images from all over the country, from large fetal programs all over the country, so that we have a huge range of imagers and imaging expertise and different ultrasound machines that we're going to also train and test the model. So we're working on that issue of overfitting and bias by enriching our data set from all of these other places. I hope that answered your question.
So then Dr. Mel Hyman asked a question: how close are we to apply AI to allow clinical providers to use physician extenders more in clinics, especially in outreach clinics or developing countries, as you implied, to provide care for patients?
Yeah, very close. The video that I showed at the end, it's commercially available. I've seen it. Or it's going to be commercially available, I think in September. But yeah, we're very close. Not for congenital heart disease. The heart, I think we sort of cornered the market on the heart, because as opposed to like the fetal brain or the fetal spine, the heart is moving and the baby's moving, and so it's just been I think an overwhelming task to try to even just teach the models about normal hearts, because they're so complex. But it's just a matter of time and effort. The technology is there, but we still need humans to do the training.
Dr. Fratlauke says, outstanding work, Anita. It's really excited to hear about. As you just discussed, the appeal to this is in the under-resourced areas in this country and beyond. Do you have plans as to how to fund that, how to truly democratize the AI technology?
Well, we're still in the research phase right now. On the strength of actually a preprint and her prior work, Dr. Arno was able to secure R01 funding for this research. And so to give you an idea of where are we with this is still firmly in the research and funding. Now, it should be pretty obvious that there's potential to work with industry to really much more rapidly develop this kind of technology, but we're not quite there yet. And then there will be, the field is still evolving in terms of how we deal with the FDA. The point of these types of models is they're iterative. And so by the time the FDA clears a model, it's already obsolete in our view. And so there has to be a way to account for that. And there's also the issue that, you know, we are using real patient data, and even though it's all de-identified, there are always going to be concerns about data sharing and about making public the data sets that are used for training and testing. In a perfect world, we could all make all of our imaging data sets widely available, just like the MNIST handwriting database, but we can't. And so, that's hindering us a little bit. But that said, I think, you know, we could be potentially a year or two away from using this for obstetric screening. And frankly, we're already there with a lot of the other cardiac applications. Just ask our sonographers who do 3D auto ejection fraction. You know, they just have to get the image and push a couple buttons, and the machine detects the myocardium and calculates the stroke volume for you. So we are already using a lot of this type of technology, but specifically for obstetric screening, probably another year or two, I would think.
And then Dr. Emilia Quezada has a question that I think actually reiterates something about Dr. Lauke's question too, that I'm not sure you've totally addressed that. Thank you for this amazing presentation on such an interesting subject. Can you give your thoughts on how costly, expensive this technology will be, or just a prediction on how available this would be in low-income settings?
Mm-hmm. Thank you. I mean, I'm doing it for free. The expense is probably in the ultrasound equipment and not in layering AI software over the ultrasound equipment. So the expense is going to be in the ultrasound equipment, but that would have been there anyway. You know, that's going to be up to the commercial people, how much they charge for something like this versus how much it actually costs is two completely different worlds. Ideally, I think that once it's developed, that it should be something that we can disseminate widely, as long as we have the ultrasound machines and at least some basic training programs in areas that don't already have sonographers. But I mean, I've seen ultrasound screening papers from, there was one several years ago from Nigeria, Thailand. The availability of ultrasound is becoming much more ubiquitous. It's the personnel, the expertise of the personnel that has been really sadly lacking for a lot of these underserved populations.
And then, are you worried, or all this comes from me, that if your diagnostic accuracy improves in these poorly resourced environments, but there isn't actually the ability to get the care, that you create almost a bigger problem than what you set out to solve?
That is the first time anybody has made me think about that. Honestly, that's a really good point. You know, how are we going to go the next step? So if somebody fails screening, then what do we do? And what do we do about that access to care? I think that we're sort of there already in the US. We already know that there's issues with access to care for women who have fetuses that are prenatally diagnosed with tetralogy of Fallot and transposition of the great arteries. There's been some really excellent work done by our Fetal Heart Society colleagues and Shab Pevandi and Martina and the biostatistics and epidemiology people here at UCSF are really leading the field in identifying what are the barriers of care and what is the effect of it. What we're going to do about it, I don't know. That's not my area, but the thing that I can do is make the model as good as it can possibly be, so that the sensitivity and specificity make sense, and so that we can start to do cost analyses to find out where to put the cutoff for the machine prediction. Ideally, we would want 100% sensitivity and a reasonable enough specificity that we don't stretch the healthcare system ability to deal with all the false negatives. But that's something to think about. I think once the model is more fully developed, is where would we set the prediction thresholds in order to make this clinically useful without causing more harm than good.
Then there is two more questions. One is, Phil Moore, is there a way to drive this AI software to open source availability rather than commercial ownership by US companies, which presumably will be used to increase cost to patients / profits for companies? I don't know if you saw, there was a really interesting article in the New York Times last weekend on this whole idea of open source AI, and it was more about language processing, but do you have thoughts about that?
At least in the next 5 years, I don't see a way to do this effectively the way we want it done without having the software on the ultrasound machines. This is really it's a point of care, issue, and so the patient and the person doing the ultrasound really need immediate feedback, both about completeness and quality, and whether or not it's normal or abnormal. And so the model has to be on the ultrasound machine, which is why I talk about partnering with industry. You could imagine say a cloud-based service where the images are sent to the cloud and analyzed, and then the answer is sent back. But for me, I think that would already exclude a huge number of people, a huge amount of population that doesn't have easy access to unlimited bandwidth and cloud-based services. So yes, I think it would be possible. No, I don't think that it would actually accomplish what we're trying to accomplish.
Thank you. Just for people who are interested, there is a company or an organization called nonprofit organization that's funded by profit organizations, very complex, called OpenAI. It's not about medical diagnosis, but it talks a lot about the ethics and the complications of making this open source. Haitum says, great work as usual. Do you think that we will need to train the model in the community rather than in the university setting?
Yes.
Well, that was a quick and concise answer.
That shows me. Thank you, Hytham. That shows me that you understood everything in my presentation. That's a very good point. Yes, we need to move away from the ivory tower. Our images tend to be much more clear, and our patient population is hugely enriched for abnormality, and so it's kind of easy to show that a model has high sensitivity when you're training with this kind of data set. So we do need to move to a broader scope, preferably population-based training and testing.
Great. Well, it's 1 o'clock and there are no more questions, at least not for now. So I want to just thank you for really a very fascinating talk. And for sharing this with all of us. And I assume we'll see you back in a year or so to tell us about what is new and further happening in this field. Thanks so much. Have a good afternoon, everyone.
Thank you.